This is problem 43. In this problem, an electron in the first excited state of hydrogen decays to the ground state after, on average, 1.6 nanoseconds, emitting a 121.5 nanometer photon. What is the minimum uncertainty in the energy of the first excited state? So for part A, we have the uncertainty in energy is approximately equal to h bar over 2 times sigma t, and sigma t is 1.6 nanoseconds. So this is h bar. We can look up in the appendix in the back of the book, and we get 0.658 times 10 to the negative 15th electron volt seconds. So we have 0.658 times 10 to the negative 15th electron volt seconds divided by 2 times sigma t, which is 1.6 nanoseconds. And this gives us 2.056 times 10 to the negative 7th electron volts. That's our answer for part A. For part B, we are asked, based on this uncertainty in energy, what is the uncertainty in the wavelength of the emitted photon? This variation in emitted wavelength is termed the natural line width. Hint: take the derivative of the relationship between the energy and wavelength and interpret the differentials as uncertainties. So we know the energy of a photon is equal to Planck's constant h times the frequency, and the speed of the photon is equal to the frequency times the wavelength. So the frequency is equal to c divided by the wavelength. So with this and this, I can say the energy is equal to hc over the wavelength. Now, the hint was to take the derivative of this relationship and interpret the differentials as uncertainty. So I want the derivative of E with respect to the wavelength, and actually all I need is the absolute value of that. So if I take the derivative of this with respect to the wavelength, h and c are constants. If I take the derivative of 1 over lambda with respect to lambda, I get negative 1 over lambda squared. But since we're dealing with uncertainties here, we just want the absolute value, so that's over lambda squared. They said to interpret the differentials as uncertainties, which means this is sigma e over sigma lambda. And we want to find the uncertainty in the wavelength. So from what we have here, the uncertainty in the wavelength is equal to the uncertainty in E times the reciprocal of this. So lambda squared over hc. I found the uncertainty in the energy up here. So this is 2.056 times 10 to the negative 7th electron volts. They gave me the wavelength, that's 121.5 nanometers divided by hc. So if we go to the appendix, we have hc is 1240 electron volt nanometers. So this is divided by 1240 electron volt nanometers. I have electron volts here canceling with electron volts in the denominator, and I have nanometer squared divided by nanometer, so that's going to give me the answer in nanometers, and this is 2.46 times 10 to the negative 6th nanometers. And there's our answer for part B.